Okay, so this video is 7.2c, and this section, there's another technique of finding the volumes of solids. The major difference is that in this topic here, we are not rotating a planar area, but instead what we are doing is we are cutting up a solid object into cross sections and adding the volumes of each cross section to get the volume of an entire solid. So again, there isn't an axis of rotation or anything like that. We are just looking at solids that have known cross sections. So the first example I'm going to do is that for a cylinder, because we know what the answer for that is. Okay, let me go snip that guy. And back from kindergarten, we know that the volume of a cylinder is equal to pi r squared h. Okay, and where does this come from? Okay, so if you take a look at this and you kind of cut this up into known cross sections, so I guess I can't draw. Wow, got the shakes. Right, so here's a thin disc that you've cut out of the cylinder. So imagine cutting disc like this through the entire cylinder. Okay, and you know that the volume of the disc is going to be pi r squared, and the height of the disc in this case we're going to call it delta y. Okay, it's delta y. And in the topic on volumes of solids with known cross sections, what you're doing is essentially divvying the solid up into several discs and then just adding them up. Okay, just adding them up. And you know addition is nothing more than integration, okay, from our Riemann sum stuff. Okay, so the volume of the cylinder can be expressed a la calculus as pi integral r squared dy, and again this is your y-axis here. You're going to go up from 0 to h. Okay, that's the height of the cylinder. Okay, so you're going to go from 0 to h. And as far as the integral is concerned, r is just some constant, okay, some radius. So then this becomes pi r squared y from h equals from y equals 0 to h. Plug and chug, and you get pi r squared h. Wow, it's not rocket science. We knew this back in kindergarten. Okay, we knew that back in kindergarten. But here is the actual derivation of the volume of a cylinder of known cross section. The next example I'm going to do is the volume of a pyramid, which you should also know from kindergarten. Okay, from kindergarten. So here's the diagram. Let me make sure this guy's shut out. So here's a pyramid. Okay, here's a pyramid of some sort. What is Kermali's rendition of it? Certainly not the Egyptians. Let's go snip this guy. And the answer for the volume of a pyramid from kindergarten is 1/3 base area times its height. Okay, so this B is the base area. So if you take a look at this pyramid here, what I've done is I've cut out a slice there. Okay, cut out a slice there. So really it turns out that it is actually a wafer. Okay, if you want to think about it, it's a wafer. And as you take horizontal cross sections of the pyramid, you're going to get wafers with different sides of the square. Okay, the base of the square has sides A. Okay, sides A. So that's the base of the pyramid. Okay, but anywhere else, it's going to be the sides are going to be S. Okay, S by S. It's a square pyramid. So we know that the volume of this wafer is s squared delta y. Okay, oops, quite what I wanted. Is s squared delta y. Okay, because remember the volume of a prism is length times width times height. So the length is s, the width is s, the height is delta y. Okay, and now I'm claiming that at a height y from the base, this is true. Should I explain this to you or let you figure this out? Since you are seniors, calculus AP, you should be able to figure that out. And I'm going to venture that, actually, you know what? I'm going to let you do it. Okay, just sweat this out. I'll just give you a hint that you're going to use similar triangles. Okay, so the volume that we want for the pyramid should be equal to, so volume, the pyramid is going to be integral a squared over h squared h minus y quantity squared dy. Okay, and my limits are going to go from 0 to h. Okay, 0 to h. And I know that a and h are constant as far as the integrand is concerned, so I can take that out and I get 0 to h, h minus y quantity squared dy. Let's see, how do you want to do this integration? Do you want to do it with foiling h minus y quantity squared and then doing each one of the pieces? Do you want to do a u sub? My tendency is to do a u sub. That's what I would do. So I'm going to do a u sub. Let's just do it, see if it works. If it doesn't, well, we'll go back and redo it. So let h minus y equals u. So minus dy equals du. And so my integral now becomes a squared h squared. Integral, it's going to be u squared, and in place of dy I've got minus du, so I'm going to put a minus sign here, du. And notice I got to change the limits of integration now. Okay, I got to change the limits of integration because these limits are pertaining to the y variable, whereas I have a u variable. So when when y equals h, u equals 0. When y equals 0, u equals h. And I know from way back in chapter 4, I can rewrite this as from u to 0, u squared du. Okay, in other words, when you change the limits, you need to stick a negative sign, but there's already a negative sign there, so that becomes a positive. And if I just go do this, did I say a u here? There should be an h. Okay, so when h was, let's go back and review this. So this is h, yeah, it's h. This is h, I guess that's where I got confused. Okay, and go chug this, and you get a squared, h squared. Can make my h's look like h's, and this would be h cubed over 3. So then this guy becomes 1/3 a squared h. Okay, 1/3 a squared h. And notice that what we have is this guy here. That's the base area. It's the base area. And so that is indeed what I had way out at the beginning. Okay. So again, another formula that we take for granted since kindergarten, and lo and behold, the understandings are not there until senior year, and that too in AP calculus. Okay, so you can see the importance of calculus. Need I say more? Need I say more? This is really amazing stuff. Okay, bye. Oh wait, I have another problem still to do. Let me pause that and go review that problem. Okay. So the last problem I'm going to do in this section is number 61 on page 465 from your textbook, okay, part A. So let's go take a look at what the problem is all about. And here's the problem, okay, number 61 right there. Okay, and I think one of the hardest part in this section, in some ways I think this section tends to be harder, and I can understand why. it's really hard to visualize the objects that you're looking at. And clearly, I think if this diagram wasn't given, it's impossible for me either to see what's going on here. Excuse me. So in 61, you're trying to find the volume of this blue solid that is described by having a base that is bounded by the graphs of y equals x plus 1 and y equals x squared minus 1, with the indicated cross sections taken perpendicular to the x-axis. So our integration is going to be along the x-axis, okay? And so I'm only doing part A. Part B is very similar, and you guys can pursue that, okay? So just to kind of see what's going on here, here is the graph or the curve y equals x squared minus 1. That's that one there, okay? And then the line y equals x plus 1 is this, maybe I should use black, is this line here. Okay, so that's this line here. And so if you take a look at the cross section ends up having one point on y equals x squared minus 1. The other point, I have it reversed here now in color, so the other point is out here, okay, on the line y equals x plus 1. And then what you've got is you've got a cross section like so, okay. And so the assumption here is that the cross section is a square, and its width, okay, again it's a wafer, so its width is going to be delta x. It's going to be delta x. So here's the complete worked out problem, and I'll kind of walk you through it, but I'll give you a minute to copy this down, okay? Maybe you might want to copy it down so you can see what's going on. Particularly the drawing is, I don't know, it's Karmali's rendition again. And as you can see in red, I've kind of disowned the squareness of that wafer, okay? The squareness of that wafer. So I'll pause and let you take this down for a minute, okay? Okay, let me go snip this and try and explain this a little bit more. I need to undo this snip and then redo this snip. Okay, so again, like I told you, one point sits on the graph y equals x squared minus 1. The other point sits on the line y equals x minus 1. Okay, and in some ways you can see the waferness of this, okay? So you're cutting cross sections vertically through the solid object that you see there, okay? And they're going to be squares of different sizes, obviously. As you move closer to the apex here, the squares are going to be smaller. As you move further away, the squares are going to be bigger. But each square is going to have one corner on the graph y equals x squared minus 1. The other point on the other corner on y equals x plus 1. Okay, so if you take a look at the length of the side of this square, that length is given by this, given by that. Because the length, notice how the x's are going, okay, they're not quite conventional. The y-axis is going this way. Okay, and the x-axis, let me go customize and get yet another color in here, and maybe I will go line. Okay, the other axis is going, the x-axis is going this way. It's not quite your convention. Okay, so since this distance here is along the y-axis, okay, I should have used a different color, shouldn't I? Let's go customize my fuchsia back. So this color here, okay, that's the the side of my square, okay, and as you can see, it is along the y direction, so it's going to be the difference of the y coordinates on the 2 points, okay. So the y coordinate on point B is x plus 1, the y coordinate on point A is x squared minus 1, okay. And so that's the length of the square. The volume of the wafer, again, is going to be the side squared, okay. So it's going to be this thing squared times the width of the wafer, okay. And if you reduce this and do a simple algebra, you get this as the volume of the wafer, and then we need to find the integration limits. So the integration limits are going to happen from the intersection points of the two graphs. So they're intersecting right here, and then somewhere way back there where the graph here, the parabola, kind of curves back around, okay, curves back around. So if you set the two y values equal, as shown here, okay, the two y values equal, do your algebra 0 stuff, and you find that your x goes from -1 to 2, and that's your integration limits right there, okay. Then your integration limits right there, and then you guys all know what that is. My favorite quote, JDI, okay. And notice that there's some statement here about n boxes, okay. All right, originally when I did this notes about a summer and a half ago, when I first started teaching calculus, this was really meant for CP Calc, and I've never reached chapter 7 in CP Calc, and I probably won't. So this is not for you. This is not for you, okay. You guys beasts, so go do this out, work this problem out, get the answer to that, and then go back and check your answer at the back of the book. Since it's number 61, it's there, okay. I'll just give you a quick preview of what it is, and here's the simple. Well, I think at this point here, calculus is over, okay. I'd say calculus is over there. After this, these three integrals, I don't call that calculus anymore. I call that baby calc, okay. And then of course this is kindergarten stuff. All right, so this was the last problem in the section on volumes of solids with known cross sections. So that takes us to the end of 7.2. So this was 7.2c, and so you could review these videos. Okay. All right. Bye.